All right, so example 4 talks about market share. Now, if you don't know what market share is, I've included a link at the bottom of this example. So if you're on the digital file, you can just click that and it has a really nice video of what market share is. And if you are on a hard copy, then you could just type that into your URL bar. So it says, suppose that after a company introduces a new product, the number of months M before its market share is S% can be modeled by that equation. When will the company's product have a 35% share of the market? So like I said, if you don't know what that market share is, you can go to that website. But essentially, it's like a certain product having a certain percentage of sales in the overall market. So for example, if you looked at iPhone sales in the total market of cell phones, you might say that like Apple or iPhone owns like 20% of the market share, because if you take the total Apple sales and divide that by total cell phone sales in general, they might own about 20% of the market. So this question is asking, when will that company have a 35% of the market share? So essentially, we are just plugging in a value of 35 into S. So if we simplify that, that's going to be 20 times the natural log of 40 divided by 5, which is 8. And that is just something you can throw into your calculator. I went ahead and did that, and it is approximately 41.6. So what does that number mean? We always want to try to explain to the best of our ability. So we can say the market share will reach 35% after about, I'm going to round it up, 42, and then we want to make sure we have the right units. It says M is months, so 42 months. Okay. So example 5 says, the expected lifespan of people in the US can be modeled as a function of their year of birth. Refer to the table below to answer the following questions. I got this data from the National Center for Health Statistics. So hopefully you've been following along in the other videos and you've seen regression now. I'm not going to show you regression on the calculator because I feel like we've gone over enough examples. However, this one, if you want to do a logarithmic regression on your TI calculator, that's going to be the button. It says 9, and it is ln reg, and that's for the natural log. So you want to do everything the same, plug in your values, but instead of doing like a linear regression or an exponential regression, you're going to hit the ln reg. So I went ahead and did that, and I got the equation f of x is equal to 8.7744 plus 14.907 times the natural log of x. So there is our function there. Try to replicate this so that you get the same equation. And if you don't, maybe come in and see me and we can chat about that. So B says, use your model to estimate the life expectancy in the year 2030. And remember that X is the number of years after 1900. And so we want to do like 2030 minus 1900, and that is 130. So that means that we want to evaluate f of 130 into our function from part A. So we'll have 8.7744 plus 14.907 times the natural log of 130. And I have gone ahead and plugged that into my calculator, and that is approximately, I'm going to round it to maybe 1 decimal place since that's what we have in our table, 81.3. Now that is our estimation using our model that we did through regression. Let's see what the actual value was in our table. So for the year 2030, the life expectancy of someone born that year is 81.7. Our estimation was 81.3, so that is pretty close. So good job, us. The expected, or the estimated life expectancy for someone born in 2030 is 81.3 years of age. All right, so let's talk about properties of logarithms now. I have taken this neat little graphic to talk about 4 properties of logarithms. There is the product rule, the quotient rule, the power rule, and the property of equality. Go ahead and look at those and then look at the examples to the right. For example, here we have log base 3 of 9x. And what we can do is we can split that into 2 different logarithms. So if you have multiplication on the inside of the logarithm, there's a rule that says that we can split that into an addition statement. So then that turns into log base 3 of 9 plus log base 3 of x. And you can read over the other rules as well. Maybe the other one I want to go over is the power rule. That one becomes very important in a lot of the real life example applications that we're going to end up solving. So maybe I'll talk about that one too. So that one says, like, if you have something like log base 2 of 8 to the x power, what we can do is we can take that exponent and we can bring it on the outside and have it become a multiplication statement. So these 2 things are equal, which it doesn't seem quite clear right now why that's helpful for us, but it helps us when we're trying to solve scenarios where our unknown variable is in the exponent. If we're able to bring it outside, that makes it easier for us to solve for the unknown variable. And I'll talk about that more in some later examples, but let's now use these properties to solve some of the following examples. So example 6a says solve for x. Now notice that we have log base 2 of x minus 5 plus log base 2 of x minus 8 is equal to 2. And because both of the bases are the same and they're being added, we could use the product rule that we saw earlier, the one right here, and we can combine that into one log statement. So we could say log base 2 of, and then the things on the inside, we can multiply them together. Now, it might not be immediately clear why that's helpful to solve for x, but from here, we can change this into an exponential statement. So B, A, E. So if we change that to an exponential statement, we get that 2 to the second power is equal to x minus 5 times x minus 8. And now that's just, if we simplify that, that's going to become a quadratic. And at this point, we've solved a lot of quadratics. So let's go ahead and FOIL out the right-hand side. So we'll get 4 equals x squared minus 8x minus 5x plus 40. Okay, so from here, I'm going to subtract 4 on both sides. And if I do that, we end up getting x squared minus, I'm going to combine those 2 x terms to get minus 13x plus 36 is equal to 0. Now, that is actually factorable. So if I make my x and I put negative 13 here and 36 here, I want to find 2 numbers that add to negative 13 and multiply to 36. And the 2 numbers that are going to do that for me are negative 9 and negative 4. So that means that this is going to factor into x minus 9 times x minus 4 is equal to 0. And I can use the zero product principle to solve for both of those, and we get x is equal to 9 and x is equal to 4. Now, we have to be very, very careful. And why is that? It seems like we're done, and that's going to be the end of it, and we have our answers. However, if you remember when we were graphing log base 2 of x, I told you that when you're thinking about the domain of a logarithmic function, you cannot take the log of 0 and you cannot take the log of a negative number. So the domain for a regular logarithmic function is going to be not including 0, but everything between 0 and infinity. So what that means is the x values that we get, we have to plug them back into our original equation to make sure that we don't get negative values. So if I plugged in 9 into my original equation, then we would get log base 2 of 4 plus log base 2 of 1. Since both of those are positive, that's okay. However, if we plugged in 4 into our original equation, we would get log base 2 of 4 minus 5, which is negative 1. And this is undefined. So what that means is in reality, x equals 4 is not one of our solutions, and really our only answer is x equals 9. So you definitely always want to, after you get your answers, plug them back into the original equation and check that all of them work. And if not, your final answer is only going to be the ones that are in the domain or the ones that work.